Chapter 6. Chemical calculations. All the utensils together. All right, so in this chapter, we're going to take what we've learned about after balancing equations and make it useful. I mean, up to this point, balancing equations are interesting because they tell us what the reactants are, what the products are, how they relate to one another. But if you can't use it for anything, then what's the point? I mean, not everybody gets excited about balancing equations or just theoretical chemistry of any kind. We want to do something with it, and that's what we're going to work with today. We need some, oops. I think we can do without that. I'll do is actually leave the meeting. There we go. No, I don't need to take that. Okay. So what we need is a way to quantify each of the elements that are participating in the reaction. And the way that's come out of decades of argument and trial and error is, to begin with, the atomic mass unit. Now, to be sure, the atomic mass unit is useful only for those who are active at the most fundamental levels of chemistry. We're gonna segue this into a more useful unit of measure, but we're gonna start here because, and have we talked about atomic mass unit before? Briefly. Okay, good. As usual, I get confused between here and my other dozen courses. Okay, so you know what the atomic mass unit is for each element. The atomic mass unit for a formula or a compound is just the summation of all the individual mass units. If you have one of them, it's just the value for that 10 atom. And if you have two of them, you just multiply 2 times that, and you get that from the periodic table. So remember, every one of the elements has a fractional atomic mass unit, except for carbon-12, because that's the standard. So carbon-12 has an infinite number of zeros after its decimal if you want it, for that isotope. The rest of them are fractions. Now, they may round off to zeros, but believe me, if you go out far enough, you'll start getting non-zero numbers out there. This work better? Not much. Okay, so the atomic mass unit for this formula unit, and we say formula units for ionic compounds, and we say molecular units for covalently bound compounds. Like we would say molecular formula for water is H2O. The formula unit for tin fluoride, tin 2-fluoride, is SNF2. Okay, so what's the formula mass for H2SO4? All we have to do is add up, right, 2 hydrogens, and these are all atomic mass units. And 1 sulfur, I have to look that one up, 3206, I think. Correct me if I'm wrong. And then 4 oxygens. And these are, I always round off to 2 decimal places, because that's sufficient for our work. And then we just add those together. And in the interest of time, I think it's 98. Yeah. add that up. That says 98. This would tell us 98.08 probably. 2 plus 6 is 8. 4. 2 and 2 is 4 and 4 is 8. Yeah. So the authors of this slide rounded off to whole numbers to get that value. I got a new marker. It's darker, but it doesn't want to erase as well as the others, which is probably better. Okay, so now we come to the concept of the mole. We didn't talk about the mole yet, did we? Okay. So the mole is just a number. Now, to be sure, it's derived from reality, but the mole itself is just a number of things. In chemistry, it would be the number of atoms, the number of ions, the number of formula units could be a mole. And it has this value rounded off to 3 decimal places. 6.022 times 10 to the 23rd. So it is a huge number, but it's still a number, right? We could have, for instance, a mole of chickens. There'd be a lot of chickens, but it's still a mole. Now, the value itself is based upon that isotope of carbon. So when you have exactly 12.000000 infinite grams of that isotope, you have exactly this many atoms in it. Okay, that's the anchor point. And the way it's actually defined is that many atoms of this isotope makes up 12 grams. Now, the nice thing about that is, if you look on the periodic table, you'll find the atomic weight for each element is in, let's see, on that periodic table, it's in the upper left-hand corner. It's somewhere in that little square for each element. That value could represent 2 different things. It could be the average, the weighted average of all the isotopes of that element in terms of how much does one average atom weigh in atomic mass units. But it also means if you have a mole of those atoms naturally occurring, including the mix of isotopes, that you will have that mass in grams is 1 mole. Now that is useful because we don't have a balance that will weigh in atomic mass units. Right? Our balances weigh in grams, typically. So if you know you have a pure element, purified from nature, so it'll have a mix of isotopes, and it weighs, and it's oxygen, then if you have 16.00 grams of oxygen atoms, you will have 1 mole of atoms. That probably wasn't a good example because oxygen occurs like this, remember? Okay. So instead of 16 grams, that would be 32 grams. Would be 1 mole. Okay. So the nice thing about that is, notice you've got a conversion factor. If you have something different than 32 grams, you can find out how many moles you have by using that ratio. And we'll do that. Trust me. It's on the agenda. Okay. 1 mole of X, right? Obviously, 10 to the 23rd. They rounded off to 2 places here. So the term for that mass that I was discussing, grams per mole, in each one of those squares is known as the molar mass of that element. And is numerically equivalent to the atomic mass units for one atom, one average atom, right? And of course, there's no such thing as an average atom. It's an average. I mean, it's mathematical, right? Actual atoms have a value, and carbon is going to be 12.0000 atomic mass units, but everything else is going to be fractional. And the average atom is a weighted average of all the isotopes. Okay, back to this topic. So if we know the molar mass of each of the elements in a compound, in a formula, then we can find out the molar mass of that compound. That is, if you have a mole of this formula, it weighs 44.01 grams because we added 12 carbons, and we use 12.01 because this is not isotopically fixed. It has a mix of 12s, 13s, maybe a few 14s. But this value is for carbon, naturally occurring carbon in nature. So it has a mix of isotopes. And then you add 2 oxygens and you get that value for carbon dioxide. That's the molar mass of that formula. So it works for molecular compounds, it works for ionic compounds, it works for any formula unit. Okay. And like I said, the conversion factor, if we say that 1 mole equals this many grams, 1 mole equals that many grams, remember, whenever you have an equivalence, you've got a conversion factor. So the conversion factor doesn't have to be 14.01 grams per mole. It could be 1 mole per 14.01 grams. It depends on the conversion that's required. Okay, we'll do some examples. In fact, we'll do one right now. So what's the mass in grams of 2.5 moles of this formula, ethane? So if you're starting off with, let's see, should I write it here? If you're starting off with 2.5 moles and you want to end up with grams, then you need a conversion factor that cancels the moles and leaves you with grams, correct? Okay. Whenever you see grams and moles in a quotient relationship, molar mass every time. So what's the grams per mole of that compound? Well, it's 2 times 12.01 plus 6 times 1.01. And that will give you the molar mass of that compound. Well, there it is. In better detail than I could do. Now I've got a ghost on my screen. So this is the relationship. You needed moles on the bottom, grams on the top. And that says you have 75 grams of ethane if you have that many moles of ethane. And we're sticking to our guns here. 2 significant figures, 2 significant figures. Conversion factors are exact numbers, so they don't count. They don't count in terms of limiting your significant figures. Okay, now, why are we doing this? Well, I'll give you a heads up. When you balance an equation, what are you balancing? You're balancing numbers of atoms and compounds in that formula. You're not balancing mass. Okay? So if we're going to talk about throwing X grams of this reactant and Y grams of that reactant together, and we're getting Z grams of a product, we can't do that directly from the balanced equation, but we need the balanced equation to get there because that defines how the reactants behave with one another to produce the product. But in order to find out the mass going in and the mass coming out, which is basically the definition of stoichiometry, you have to be able to convert moles to grams and then grams back to moles, or the other way around. See what I'm getting at? It should become clearer once we work a problem or two.
Where does the 30.07 come from?
It comes from 2 times 1.01 for that, plus 12.01, and 6 times 1.01. That should equal 30.07. Now, this is the molar mass of that formula. That one that actually works. Okay. How about the number of moles of 50 grams of water? If you have 50 grams of water and you want to convert to moles, you need to cancel the grams and leave you with moles. That means moles is on the top, grams on the bottom. So your conversion factor would be 1 mole per so many grams of water. So you would say 2 times 1.01 for the hydrogen, and then 16 for the water will give you 18.02. 1 mole per 18.02 grams, multiplied by that. Here we go. So the grams of water cancel, leaves you with moles of water, and there's your value. Okay. Now, I think we're throwing this one in here simply because it's a bigger molecule, right? And what I'm trying to show here, and what the authors are trying to show, is this scales up to as big a molecule as you want. Some molecules are huge, but you calculate the molar mass exactly the same way. You just add up 9 times 12.01 plus 8 times 1.01 plus 4 times 16. And you get a molar mass for aspirin. Acetylsalicylic acid, if you're interested. So the question is, what's the mass of 1 mole? Well, we just added it up, and it turns out it's 180 grams. Now, strictly speaking, I wouldn't throw that 0 away. Right? I'd put a decimal there and preserve that value. But roughly 180 grams for 1 mole of aspirin. Okay. When we present a chemical formula, we can interpret it in 2 different ways. One is we can say that's what 1 molecule looks like. It's got this many atoms of each element in it. Now, that's a valid statement for molecular compounds like N2O4, where they're covalently bound. It's kind of a stretch to go to ionic compounds because we know ionic compounds are a network of positives and negatives. So we have to sort of stretch our imagination there. But at the microscopic level, that's the simplest whole number ratio of elements in a compound. This has 2 atoms of nitrogen, 4 atoms of oxygen. Right? But it also means that in 1 mole of that compound, you have 2 moles of nitrogen and 4 moles of oxygen. Right? So the ratio is the important part. If we had 2 moles of this, right? If we had 2 moles, we would have 4 moles of nitrogen and 8 moles of oxygen. Okay? That's important to recognize when we start using balanced equations, because we do have coefficients. And the coefficients tell us either how many molecules there are, reactant or product, whatever the case may be, or how many moles there are. It's valid for either. And since numbers of molecules, moles of molecules are still numbers and their ratios in that balanced equation, that coefficient means the same thing, whichever interpretation you want. Okay, so how many moles of carbon atoms and hydrogen atoms are present in 2.5 mole sample of C2H6 or ethane again? It is 2.5 moles of that unit. Then we have 5 moles of carbon and 9 moles of hydrogen. Oh, excuse me. No, we have 15 moles of hydrogen. Okay? The ratio is the important concept here. The ratio within the formula is where we're at now. But when we get to balanced equations, we're going to find that the coefficients of the compounds and the reactants and products, those ratios are also valid for going the next step. And I'll give that to you as we get to it. How many moles of carbon atoms, hydrogen atoms, and oxygen atoms are present in this formula? Well, 9, 8, and 4, right? That's how many moles. Okay, so this, I wouldn't get too bogged down in this thing right here because the methods that I'm going to show you have this built into them, right? And unless you just really love these flow diagrams, then just take them at face value and move on, okay? But you can make conversions, right, between any of these. I've got, oh, I didn't name it, did I? 6.022 times 10 to the 23rd is also called Avogadro's number, after the Italian. Let's see, at that time, they weren't called chemists. They were natural philosophers. So Avogadro, now, Avogadro didn't present that number to the scientific community. It came later. But the concepts that he championed are the basis for the validity of that number. So he's honored with putting his name on the number. All right. Yeah, like this works, but conversion factor approach I like better because it's more flexible. You say, where am I? Where do I want to go? The conversion factors will be whatever you need to get there. Okay. That's what I mean by conversion factor approach. What you're given, where you're headed, your conversion factor or factors go in here. Like I said at the very beginning, lots of chemistry problems can be solved simply with conversion factor mathematics. Dimensional analysis. As long as you don't violate any chemical laws. Okay. So, did I do one of these before? How much will it cost to drive from Beckley to Atlanta, Georgia? I used to do this calculation fairly often when I was visiting relatives down there a lot. Right? What are you given? Well, I would say you're given how far is it? Right? That's basic. How far is it from Beckley to Atlanta? And then that's how many miles. The question is, how much will it cost? That's your target. You need dollars. So if it's so many miles, what else do you need to know? How many gallons of gas do you need, right? So you need to convert miles to gallons, right? That's the gas mileage of your car. And then you need to convert gallons of gas to dollars. That's a little tricky right now because the prices are, California just broke $5 a gallon average. So the distance from here to Atlanta, well, from Beckley to Atlanta, is 385 miles. Right? And there's your target. Right? So we need a conversion factor. That's pretty generous. My vehicle probably won't get that, but it's easier to deal with that number than it is with 22.5 or something. You put that in there for your car. Your car might get better than that, right? If you have a small 4-cylinder engine, you probably do get better than that. And then at the time this slide was created, gas was $2.80, right? We'd love to be back in those days. We could be, right? All you have to do is open the spigots, right? First thing Biden did when he came into office was shut us down energy-wise, right?
I think you just shut down more pipes too.
Shut down what?
More pipes that are transferring gasoline and oil.
Yeah, pipelines. Yeah, sure did. Thank you, President Houseplant. Okay, so this says that I'm going to need minimum $43 to get to Atlanta, and then double that to get back. And then Atlanta's a big place, so I need some buffer to drive around money. So that's what I mean by the conversion factor method. Which of the following is closest to the average mass of one atom of copper? This is kind of a dumb question, right? Because do you know any copper atoms that weigh tens of grams? I don't. They're a lot smaller than that. So you can just say, there it is, by process of elimination. But we can calculate that value. Well, we didn't, but we can. We'll use, why don't we do that? What does one atom of copper weigh? All right, so you're starting off with one atom of copper. And you want to end up with mass, grams. Well, one conversion factor won't get there because we know conversion factor from numbers to mass, molar mass, requires that we have a mole here, right? So what we need is another factor like that. And we know that atoms and moles are related by Avogadro's number. Then we can get rid of atoms. Now moles, we need so many grams per mole. So copper, we have to look up the periodic table. 6355. Okay, then that cancels moles and leaves us with grams. So this is what I call the thinking part. This is where you put your thinking cap on, set it up right, be sure that all the dimensions cancel out and leave you what you want. Then the rest is number crunching. So you say 1 divided by that number times this number gives you your answer. And that should be your answer right there. There should be several of these in your homework exercises to give you practice doing. How about the number of copper atoms in 63.55 gram sample of copper? This is sort of a trick question too. Okay. If you know that one mole of copper weighs that, which it does, then you know that it has to be 6.022 times 10 to the 23rd atoms. That's it. No calculating required, just logic. Okay. Now, as is my trend, get more complicated as we move along. if we have 100-gram samples of each of these elements, magnesium, zinc, and silver, which one contains the greatest number of atoms? Okay. If each sample has to weigh 100 grams, then do they take the same number of atoms to get there? No, because they're different molar masses, right? It takes more atoms of the lightest one to get to 100 grams than atoms of the heavier one. So the greatest number of atoms will be the lightest element. Which one has the lowest molar mass? So we look at them, say magnesium is, let's see, 24.31 grams per mole. And zinc, we just did that one, 63.55. And silver is even heavier, 107.87. So we know that the lightest one is the one that takes more atoms to get to that mass. So magnesium would be the answer to that question. The one that weighs the least for each atom. Okay. Now, that was simple. Let's say we need to rank them in the order of descending number of atoms. So which one has the most, and which one has the middle, and which one has the least. You can go in and do this calculation and say exactly how many atoms of each is represented by these values. Or, if you're taking a test, you want to do it quicker than that. So, logic would tell you that what you really need to know is what's their relationship to a mole, right? Is there anyone in here that's exactly equal to a mole of atoms? Well, this one is. How about zinc? Well, let's see. Zinc, 1 mole of zinc is 65. So this one's greater than a mole, right? And magnesium is 24.3, so this one's less than a mole. Okay, so now we can put them in order. Right? Descending number. So the greater than a mole is zinc. And then there's silver in the middle. And then there's magnesium on the bottom. Less than a mole. Oh, I didn't know I did the calculation. But that's the logic behind this. Okay? Now consider 100-gram samples of each of the following. Water, dinitrogen monoxide, which is laughing gas, nitrous oxide. This is propionic acid, I think, carbon dioxide. Descending order of number of oxygen atoms. All right, so this is one of those problems. When you're faced with a complex problem, look for ways to simplify. Bust it into smaller pieces. So if we're starting off with 100 grams, we want to end up with a number of oxygen atoms. What do you need to do to get there? Well, first, I would try to figure out this 100-gram samples, what does it mean in terms of moles of molecules? I calculate the moles of each one of these. And then that means that for this one, 1 mole of water is also 1 mole of oxygen. 1 mole of nitrous oxide is also 1 mole of oxygen. That's the ratio. 1 mole of this compound is 2 moles of oxygen, and 1 mole of carbon dioxide is 2 moles of oxygen. So in order to solve this problem, I invoke I channel the ghost of Henry Ford. Set up a assembly line. Right? If you have water, nitrous oxide, C3H6O2, and CO2, and you have 100 grams each of each one. See, I'm doing the same thing over and over and over again. Right? Now I need to convert to moles of each one. Right? Grams per mole. I'm just doing it over and over again. Now there will be a difference from one to the other. Water is going to be 18.02. Right? So I give you the number of moles of water molecules. And then nitrous oxide would be 28 plus 16 is what? 44. Okay. This one takes a little more doing. I'll come back to that one. This one is 32 plus 12.01, which is 44.01, right? This one's going to be 3 carbons, 12.01. And 6 hydrogens, 6.06. And 2 oxygens, 32. So that's 74.09. Okay. So now we've come to the point where we have moles of the compound. Now that you have moles of the compound, then you can have a compound here. And oxygen on top. All right. This is 1-to-1. This one's 1-to-1. This one's 2 oxygens for every compound. This is 2 oxygens for every compound. Now we've done all the thinking. Now all we have to do is say 100 divided by 18.02 times 1. That answers that one. 100 divided by 44 times 1. 100 divided by 74 times 2. 100 divided by 44 times 2. And then we can put them in order after that. Let's see. Can I do that? There we go. Okay, so this one's going to be 5.56 moles of oxygen, 2.27, 2.70, and 4.55. So we put them in order. This would be descending order. So the first one would be this one, and that one, and this one, and then that one, in that order. There we go. So that's how I set up an assembly line. And it's usually pretty easy to recognize when you need an assembly line. Let's see, do I have, are we going to do, have we already done formulas from composition? Is that chemical calculations? Did we do that last one? I may have already showed you, so that, I guess we did. What can we do? Composition. We'll see. All right. So the formula for aspirin is this. Calculate the number of molecules in 0.325 grams of aspirin. That's the standard aspirin size, 325 milligrams. That's not baby aspirin. Baby aspirin's 81 milligrams. This is what you take if you have a headache. or high fever. It will knock that fever down. So, oh, I've already got it here. So we start off with so many grams of aspirin, and then we need the molar mass of aspirin to find out how many moles. And then we convert moles to molecules here, and that tells us molecules. This is Avogadro's number, right? It's a number of things per mole. So it could be molecules, it could be atoms, it could be ions, whatever you need. Okay. So this is just a review of chemical reactions. You have reactants and products. We've done that already, right? For balanced equations. Must have done it already. So when we have a balanced equation like this, let's see if it's balanced. 2 hydrogens, 1 oxygen, 1 calcium, 1 sulfur. Okay, it's balanced. So we have coefficients of 1, 1, 1, and 1. So what that means is 1 molecule of calcium sulfide plus 1 molecule of water yields 1 formula unit of calcium oxide plus hydrogen sulfide. Or it could be 1 mole of calcium sulfide units plus 1 mole of water yields 1 mole of calcium oxide plus 1 mole of hydrogen sulfide. The ratio is still the same. And all the atoms are accounted for in the process. Same number of atoms on both sides. Now, why is it going through this? We've already balanced equations, haven't we? Did we not balance equations yet? Oh, I'm sorry. Yeah, say something.
No, I was trying to think. I was like, I don't think so.
No, okay. Let me shift gears. Okay, so that's that was a chemical equation. Reactants on the left, products on the right, and an arrow in between. The coefficients, that is the numbers in front of the formulas, represent how many formula units go into that reactant side or come out on the product side. And let's back up. Once you've written these compounds correctly, like this, right? Calcium is a 2+, sulfur is a 2-. That's correct. Water's given, H2O. Calcium is a 2+, oxygen is a 2-. That's correct. H2S is a covalent compound. Once you've written them that way, then the only way that you can balance this equation, that is put them in order to have the same number of elements on either side, 1 sulfur, 1 sulfur. The only way that you can change it after that is with coefficients in front of each one. Right? Once you write the compound, then subscripts are forbidden. You can't touch them to balance an equation. So the coefficients are the only way from that point on. And if you write the compounds correctly, or the elements correctly, whatever the case may be, then it should balance. Right? If you write them incorrectly, then it will never balance. Okay, so once we've balanced an equation, those coefficients tell us the ratio of each of the reactants to the products. So if we're saying that 1 mole of this compound plus 1 mole of that yields 1 mole of this and 1 mole of that. The ratio is 1 to 1 to 1 to 1. And that ratio of those, whatever they might be, it could be any number. It could be 1, 2, 3, 4, 5, 6, whatever. And we always try for whole numbers. Avoid fractions. Once you know those ratios, then you know that if 1 mole of this goes in, 1 mole of that comes out. That ratio is fixed in a balanced equation. And that's how we get to masses. Because we know if we have 1 mole of this, we can calculate what the mass is. And if 1 mole of this comes out, we can calculate what that mass is. So mass of this goes in, but a different mass comes out because it's a different compound. Okay. Oh, for balancing equations. Let's see, did I? Yeah. If I get one of these. All right, helpful hint. Okay. That's not a step-by-step. Those are guiding points. First, you have to write the unbalanced equation. Right? You got to be sure that the reactants are written correctly, the products are written correctly, and most of the time, they will be given to you in even a word form, word problem, right? So if you're given the names of the compounds, then you got to be able to write those in the formula form. Otherwise, you can't balance the equation. That's why we went to so much trouble learning how to write compounds, name them in the beginning, because we're going to need them for this. All right, this is sort of generalized. Most often, what you'll see in chemistry textbooks is write the unbalanced equation and then balance it by changing the coefficients as needed, balance by inspection. That's an easy way for an author to say you're on your own. Right? But I'm not going to do that. I'm going to give you guidance. The end result of the balanced equation should be the total number of element atoms on one side has to equal the total number of that element atoms on the other side, reactants to products. That way, you're still obeying the law of conservation of mass, right? Found by Lavoisier so many centuries ago. That's why it works. Okay. These are just reinforcements, right? I just told you that one. Subscripts cannot be changed. And we try to finish off with the smallest whole number ratios. In other words, if we had, in that previous equation, if we had 2, 2, 2, and 2, we'd reduce it to 1, 1, 1, and 1, because we can divide the whole thing through by 2 and reduce the numbers, the smallest whole number ratios. Now, one of the tricks for balancing an equation there is the fractional trick. Sometimes you can use a fraction as an intermediate step, as a coefficient. And then once it's balanced, you multiply the whole thing through by the denominator of the fraction and get rid of it. And that gives you the whole number ratio. Okay? I'll show you one. What reaction's occurring, right? Sometimes we put the physical states in there. That's important. In some cases, like we would follow the compound or the element with G for gas, L for liquid, G for gas, liquid, solid. Or if it's in solution, in aqueous solution, dissolved in water, we might follow it with an AQ. Those are the only ones that we're going to be using. And that gives you the state of the compound or element as a reactant or product. Here it is, balanced by inspection. Let's see, do I have a comment on that one? No, I don't. But never change the formulas. Once the formulas are written, do not mess with the subscripts. Okay, these are those helpful hints. I just put them on here so they'd be on record, but you've got a hard copy of that. So I'm going to skip these and do examples. Let's see. This is our fractional example. Let's see. There was one in here. Let's see. This is one that I just added. if you have an equation where you've got an element that's an odd number subscript in one place, an even number subscript in another place, sometimes you can cross multiply. Just take the subscript of one, multiply by the other one as a coefficient, and vice versa. And that eliminates a lot of the fumbling around that can occur. And it takes experience. You just have to work a lot of it to know where that would be valuable. Okay, so here's an example using this hint. If you have polyatomic ions in your compounds, like this one, ammonium, and it shows up on the product side unchanged. You got ammonium over here, ammonium over there. Or you got phosphate here and phosphate there. You can use those as balancing groups. And it takes a lot of the strain out of balancing that equation. Makes it quicker. Now, if in the process, this polyatomic is broken up, sometimes that happens, and produces a different nitrogen compound over here, and hydrogens are spread out over here, or phosphorus is broken away from, then you have to go to individual atoms as your balancing groups. Now, what do I mean by balancing groups? Well, this goes to my budget method. Write your unbalanced equation here. Be sure that all your compounds are written correctly. In this case, we've given them phase indicators. And then below, on the left-hand side, you write what are each of the groups. So we have ammonia, we have phosphate, we have calcium here, and chlorine there. And then you go over here on this side and you count. How many this one, how many that one, how many that one. That's your starting position. And you go over here and say, how many on this side? And you can see, just at a glance, you can see that it's not balanced. You don't have the same number of each on either side. So once it's balanced, you should have exactly the same numbers at each one of these rows. And then you know instantly that your equation is balanced. Okay, so for this one, I'll set it up like this, right? These are initials. Right? We're counting them up now. And we're going to count these up on the product side. All right. Now what do? Now you decide where to start. Usually, if you have written all your compounds correctly, then it doesn't matter where you start. You'll eventually get there. But sometimes, if you start in one place, you get there quicker than if you start in a different place. So one of the hints is if you have an element standing alone on either side, right? We don't have that in this case. But if you do, if you have an element standing alone, save it to last. Right? Because if you put a coefficient in front of that element, you're only changing that element in your total. If you put a coefficient in front of a compound, you're changing lots of other things. And that can affect the other coefficients that you have, and you've got to go back and recalculate and do them over again. So save those elements to last. In this case, we don't have that luxury, but we do have our balancing groups here. Ammonium, phosphate, same on both sides. So where do we start? Well, I think I started with calcium, right? We need 3 calcium over here. So I put 3 there. That changes to 3 here, but it also changes chlorines from 2 to 6, right? 2 here times 3 there. You actually have 6 chlorines now instead of 2. Okay? So now that I've changed chlorines to 6, I need 6 chlorines on this side. And that also changes the ammonium group to 6. This is a polyatomic that we're using as a balancing unit. So you have to change the whole thing to 6. You don't have to count the individual atoms if you're using it as a group. Okay? So we've got this one fixed. We got that one fixed. We changed the ammonia. So how do we change the ammonia on this side? Well, if we need 6 ammonias on this side, a coefficient of 2 will give you 6 ammonia, right? Okay. It'll also change the phosphates to 2. Because there's only one phosphate here, but there are 2 formula units means now you have 2 phosphates. So we got 2 phosphates here. And if you look, 6236, 6236, we're balanced. All right. How about this one? Which of the following correctly balances the chemical equation given below? All right. First thing I would do, since this is given to us like that, I would say, all right, are the compounds written correctly? Calcium oxide, yeah, +2 -2. Carbon is a separate element. Calcium carbide, which is written correctly. And carbon dioxide, okay? We have 1 carbon here, 1 carbon there, 1 calcium there, 1 calcium there. 2 oxygens here. We need. It's not balanced yet. So what if we balance it? Calcium oxide plus carbon yields calcium carbide plus carbon dioxide. Okay, so we have calcium, oxygen, carbon. Covers everybody. 1 calcium, 1 oxygen, 1 carbon, 1 calcium, 2 oxygens, and 2 carbons. Okay, so calciums are okay. What if we go to oxygen, say that one? 2 oxygens here, 2 oxygens here. Okay, so that gives us 2 oxygens here. It also changes the calciums to 2. Okay? Notice I'm keeping this one separate. I'm saving it for last. Now we need, let's see, 2 calciums. There we go. 2 calciums changes the carbons to 4. Now we need 4 carbons. We're done. Oops. There we go. Now we're done. Did I lose anybody? Need practice. Yeah. Okay, so is this the simplest, right? 1, 2, 4, 2. We can't simplify it any further because that's a 1. So we would expect, let's say 2. Wait a minute. I did something wrong. Two calcium, 2 oxygen, 2 oxygens, 4 carbon. That should be right. Did I write them wrong? No. Oh, maybe the slide's wrong. Yeah, the slide's wrong. Okay. I need to make a note to correct that. Fix that later. It should be 2, 4, 2, and 1. Now, if it were this one, then technically that one would be correct, right? And this one would be correct, but this one is the best if it were correct. Okay, so which of the following statements is true? The number of molecules is conserved. I don't think so. What are the numbers that tell us the number of molecules? The coefficients. Coefficients could be anything. So this one's false. Coefficients tell you how much of each substance you have. That's a little misleading. How much refers to mass. It tells you how many molecules or how many moles of each thing you have. So we're going to say that one's false also. Atoms are neither created nor destroyed. That's true. Coefficients indicate the mass ratios. Nope. Number ratios, mole ratios. The sum of the coefficients on the reactant side equals the sum of the product side. Nope. Doesn't have to be. All right, so that's the only true one in the bunch. The rest of them are false. If we use our imagination and think that one's talking about mass. Okay, so if we had this description, if we heat sodium bicarbonate and it produces sodium carbonate, carbon dioxide, and water, then we need to be able to write that equation. So what's sodium bicarbonate? Well, this is what we call now a trivial name. It should be sodium hydrogen carbonate. Hydrogen carbonate is a polyatomic ion. Bicarbonate is an old way of saying it. And in fact, you'll still see it. If you go pick up a box of Arm & Hammer baking soda, look on somewhere on that label, it'll say sodium bicarbonate. So it's this, HCO3. And we heat it, and we make sodium carbonate, right, which has 2, and carbon dioxide, and water. It's going to be kind of hard to set up my budget with this one because I squirreled around. But if you work enough of these, some of them you can do without the budget. You just need to be sure that you're counting up all the right atoms, right? If we have 2 sodiums here, we need 2 here, right? So that gives us 2 sodiums. That gives us 2 carbonates. Well, actually, we can't do that. I need to set up a budget. It's not going to work like this. So let me stretch it over here. Sodium bicarbonate and sodium carbonate. Right, this is 2 minus, that's a 1 plus, so we need 2 of them. Carbon dioxide and water. Now we can do a budget. Sodium, hydrogen, carbon, oxygen. So we have 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. On this side, we have 2 sodiums and 2 hydrogens and 2 carbons. And we have oxygens, 3, 4, 5, 6. Okay. So what did I do before? I put a 2 here, didn't I? Change that to 2. That makes 2 hydrogens, 2 carbons, and 6 oxygens. So, oh, is that it? Yeah. That's all it took. 2 sodium, 2 hydrogens, 2 carbons, 1, 2, 6 oxygens, 3, 4, 5, 6. Okay, we're done. Sometimes it's easy. Okay, so we need 2 here, 1 there, 1 there, 1 there, 1 there. So C is the answer. In my general chemistry classes, first semester, we do that reaction in the lab. And we quantify each of the components. It's kind of tricky because when you're heating it up, this is a solid and that's a solid. But this one turns to a gas and that one turns to a gas. Right? So in order to tell what are these gases that are generated, you sort of have to do a little detective work. So we propose 3 or 4 different reactions that are possible. And then eliminate them logically. until we end up with this one. And then you can do your calculations. We know the mass of this going in. We know the mass of that coming out. Say, is that correct? Right. If we do the calculation, if we say we have this mass based on this formula, what should we get here? And compare that to what we actually measured. Yep, that's confirmation. Okay. This one is supposed to be balanced. 4 irons, 6 oxygen. Yeah, that's balanced. 4 molecules of iron, actually 4 atoms of iron, react with 3 molecules of oxygen to yield 2 formula units of Fe2O3, which would be iron 3 oxide, would be the name for that. Okay, so wait a minute, was there a question? There was a question there. No, there wasn't a question. 4 moles of iron produce 2 moles of Fe2O3. 4 moles of iron produces 2 moles of Fe2O3. There's an equivalence there. 4 moles of that equals 2 moles of that. Or 3 moles of this equals 2 moles of that. And using that equivalence, based upon the coefficients, we have conversion factors. Okay, so how many conversion factors could we get from this problem? Well, if this relationship, there's 1, there's 2, there's 3, right? And actually you can get 6 because if you need to, you flip it. Flip the conversion factor. Remember, conversion factors are always equal to 1. You can flip it and you can get 6, depending on which way you're going. Going from here to here, or you're going from there to there. You have to flip your conversion factor to use it. Okay. Let's see. Ethane plus oxygen is carbon dioxide and water. What are the coefficients for the balanced equation? This will be a good one. Okay, so we got ethane, C2, H6 plus oxygen yields carbon dioxide and water. Just so you know, whenever you burn, this is called a hydrocarbon. Hydrocarbon. Anytime you burn a hydrocarbon, combustion reaction, you always get, if it's complete, you always get carbon dioxide and water. If it's incomplete, like inside an internal combustion engine, you might get carbon monoxide and some nitrous oxides that are, so we're talking about pure chemistry here. This is what you can expect. All right, so let's balance this equation, right? Carbon, hydrogen, oxygen. That's all there is. So we have 2 carbons, 6 hydrogens, 2 oxygens. Notice we got an element here, so we're going to hold that one till last. We got 1 carbon, 2 hydrogens, and 3 oxygens. This would not, see, have an odd and an even. This one would not lend itself too well to cross multiply because you've got oxygen in 2 different places. So we wouldn't use the cross multiply trick. But I will show you another trick as soon as we get to it. Okay, so where do we start? If I don't have any intuition or experience knowing where's the best place to start, I just start at the top, work my way down. You'll eventually get there. So 2 carbons on this side, only 1 carbon on this side. So if we put a 2 here, that makes 2 there, plus 4, 5 oxygens. Okay. Hydrogens. We need 6 hydrogens. So hydrogens are only here. We need 3. So that's 6 hydrogens. Now we've got 3 plus 4 is 7 oxygens. Okay. Carbon and hydrogens are balanced. We've got this lone oxygen, but we only need 7 of them. If we put a 3 here, that gives us 6. Put a 4 there, that gives us 8. Right? So we can't do it with a whole number. So this is where we use the fraction trick. 7/2 will give us 7 oxygens. Right? That molecule has 2 oxygens in it. So if you take half of them, that's 1 times 7 is 7 oxygens. Okay, so now technically we're balanced, but we want the whole number ratio. So we get rid of that fraction. Multiply the whole thing through by 2. That cancels that fraction. And it puts a 2 here, 7 there, 4 there, and 6 there. Okay. Did I lose anybody? Okay. So what we're looking for is 2746. 2746. 2 moles of that produce 6 moles of water. Yep. That was the fraction trick. And just so you know, whenever you burn a hydrocarbon and produce carbon dioxide and water, you'll always use the fraction trick for some reason. The only one that it doesn't require is methane, CH4. But C2H6, 32, C3, H8, on up. You'll always use the fraction trick for those. So if you were going to burn the octane that's in your gas tank, right, that's why they call it octane rating for your engine. It's based upon that molecule. It's C8H18. And it's going to require a fraction trick to balance it. Okay, now we'll get into stoichiometry, where we actually say, all right, if I put so much mass in, how much mass do I get out? And I'm not going to stop here. It's still valid, but not useful in my opinion. This is probably, I forgot I had this one in here. This is a useful problem, but it's extremely complex for newbies. Let me see. Let me look at my hard copy and see if there's an easier one on the other side. So we'll come back to this one. Yeah, we got one at the end. All right, it's a complex problem. We break it into simples. All right, what's the question? Methane reacts with oxygen in air to produce carbon dioxide and water. So we write that similar reaction to the ethane. Ammonia reacts in oxygen to produce nitrogen monoxide and water. So we got 2 different reactions, but we're going to relate them. First, we're going to balance the equations for each of these. Okay, so this one's going to be CH4 plus oxygen yields carbon dioxide and water. This one should be fairly easy because it doesn't require the fraction trick. You've got 1 carbon, good. You got 4 hydrogens, 4 hydrogens. Okay, so that means 2 oxygens and 2 oxygens is 4 oxygens. 2 means 4 oxygens. That's balanced. Now this one is ammonia. Let's see, let's put it over here. Ammonia plus oxygen yields what? Nitrogen monoxide plus water. Okay. We got 1 nitrogen here, 1 there. We got an oxygen here, we'll leave it alone. 3 hydrogens. Oops. 3 on this side, 2 on that side. This is where cross multiply will work. So we take that 3 and put it here. Take that 2 and put it here. Now we have 6 hydrogens on both sides. We're good. But now we have 2 nitrogens here. We need 2 nitrogens there. So that means 2 oxygens plus 3 oxygens is 5 oxygens. Means we need 5 oxygens. So we use the fraction trick. Okay? Now we need to get rid of that fraction. So what we'll do is multiply the whole thing through by 2. So that makes this one 4. This one now is 5. This one is also 4. And this one is 6. Now we're balanced. Well, let's see, did I do it right? Yeah, I did it right. Okay. So let's get these out of the way. Okay. We balanced those equations. Now what? Now the question is, what mass of ammonia would produce the same amount of water as 1 gram of methane reacting with excess oxygen? So let's back up and look at it from, read it backwards. Well, not literally, but logically backwards. 1 gram of methane produces how much water? Because we want the same amount of water here as here. So 1 gram of methane produces how many grams of water? Because, let's do it this way. Produces X grams of water. We also want the same amount of water here. Right? The same amount of water as produced in that reaction must be here. Then we work backwards. How much ammonia would that require? What mass of ammonia? Okay. So once you've got balanced equations, then put the information that you know, what's given, put it where it's supposed to be relative to your equation. I usually put the starting values here, and then if I do any calculations, they'll either be down here or up here, wherever I have room. So we're going to work back to this one. Y grams. That's the grail. That's the holy grail right there. That's the answer. Right? So we obviously have to go from here over to here and find out how many grams that is. So how do we get there? Well, there's an imaginary wall here, 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 all along that equation. You can't get through that wall with mass. The only way you can get over that wall is with moles. Right? There's a guard at each gate. You can't get through with grams. You got to make moles. So we got to convert this gram to moles. 1.00 grams of methane. How many moles is that? Right? Quotient relationship, molar mass. So that's 12.01 plus 4.04, which is 16.05, right? So 16.05 divided into 1 equals what? You can check me on this. 16.05, I'll just do an inverse. Same thing. 6.23 times 10 to the minus 2. 6.23 times 10 to the minus 2 moles of methane. Now we want to know, we can go where we want to now. We can find out how many moles of water that represents. What we need is moles of methane, moles of water. Right? Moles of methane will cancel this one. Like this one canceled that one. And this will give us moles of water. So what's the ratio here? Coefficients. 2 1. So 2 times that value, 1.45, 1.25 times 10 to the minus 2. Moles of water. That is equal to this. Okay, so we want to go backwards now. How many moles of ammonia does that represent? Well, moles of water. Now we're in this equation. 6 moles of water to 4 moles of ammonia. So 4, 2/3 of that value is 8.31 times 10 to the minus 2. 8.31 times 10 to the minus 2 moles of ammonia. Okay? Now we got moles of ammonia. We just have to convert it to grams. So we need something to multiply by this. I'm going to have to wrap it around. So what's the molar mass of ammonia? 14.01 and 3.03. 1704. 1704 times that value is 1.42. 1.42 grams. Oh, it's animated. The one rule in this whole procedure that you can't violate is how do you get from one to the other? You can't do it with mass. It has to be moles. Right? Okay, so there's the conversion to moles of methane. Then we convert moles of methane to moles of water. And then we take moles of water now in a different equation and convert that to moles of ammonia, and then ammonia to mass. So we go mass, moles, moles, mass. No, mass, moles, 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 mass. Okay. It's a multi-step problem. And you just have to be extremely methodical about it. I mean, lay out your plan of attack and then go at it as if you're got blinders on. Okay, now that we know how to do stoichiometry, there's one other fly in the ointment, and that's called percent yield. Up to this point, we've been talking theoretical. When you have a balanced equation and you have so many grams of a reactant and you're producing so many grams of a product, you want to find out how many that would be. If you're just using the balanced equation, you're getting the theoretical amount. That's if all of that reactant is produced to maximum product. But that never happens. Any chemical engineer will tell you that there is an efficiency in the reaction. And it's not just the reaction, but in the process of purification too. Because most reactions don't go to completion, or they introduce contaminants of some kind. It's just a mess. So you have to purify your product. And that also introduces losses. So we invented this percent yield calculation to account for that. All you have to know is what's the theoretical yield? What's the maximum amount that you can expect from that reaction? And then actually measure what you get from the reaction under those identical conditions, and then ratio them. And that gives you percent yield. Many reactions are like 10, 15% yield, and that's considered good. The Haber process is like that, where you convert nitrogen from the atmosphere, combine it with hydrogen, and make ammonia. If you're getting 15% yield, you're doing good. Others, you can expect 90% yield. It just depends on the reaction and how good you are at producing the product in its purified form. Okay. So what will be the percent yield of a product for chemical reaction for the theoretical yield? Theoretical yield and actual yield are 5.6 and 4.5. This is the actual, that's the theoretical. So you just ratio 4.5 divided by 5.6. Right? Can't do that one. Right? Unless you put them in the wrong order. Put that one on top and this one on the bottom. That's where I see students making mistakes when they use their calculators. Right? I don't know, it's like a certain type of calculation dyslexia. You just reverse things. Say 4.5 divided into 5.6. No, it's 4.5 divided by 5.6. And then times 100. So this one can't be it. That one can't be it. It's either this one or that one. And you have to do the calculation, and you find it's 80%. Okay. Let's see. How are we doing on time? 10:30? Okay. And lab starts at 11. Yeah. I think we're going to be all right. This is the last one, isn't it? Oh, next to the last one. Concept question 1. Pennies produced prior to 1982 were composed of 95% copper. I think that's the same thing for silver coins too. Up to that point, silver coins were, I believe, 90%. 90%. They were mostly silver. And then after that, they started cladding them. They put silver on the outside and base metal on the inside. It's called debasing the currency, historically speaking, right? They turn your currency into worth less than it really is, based upon the value of the metal. But prior to this point, we had 95% copper in those pennies. On average, the pennies weighed 3.11 grams. How many atoms of copper were present in one penny pre-1982? Okay, this is a dimensional analysis problem. So what are we given? We're given 95% copper and mass of 3.11 grams. Okay, and the question is, how many atoms? Okay, so how do you get there? Well, ask yourself this. If that 3.11 grams was, well, how much copper is in that 3.11 grams? Right. 95% means what? In this case, it means grams of copper per grams of coin. It's mass. So that means 3.11 times 0.95 equals the mass of copper that's in that coin. I did something wrong. Let's try that again. No, I didn't. 2.9. When I do something like this, when there are calculations to be made, only multiply, divide, I keep all the decimal points until the end, and then I round. That avoids rounding error. So I'm going to say 2.9545 grams of copper. Now that we know how much copper is in there, we can find out how many moles of atoms and then how many actual atoms. So we have, let's see, 2.9545 grams of copper. and we're going to convert to moles. Let's see, copper was 63.55. 63.55 grams of copper, moles. And then we can convert moles to atoms. 6.022 times 10 to the 23rd. There we go. So let's see if I can estimate. Let's see, 3 divided by 60. 1 over 20. What's 1/20? 0.05. 6. It's probably 22. Oh, okay. Significant figures. We had 3 here. Oh, we're going to do it animated. That's true. We did that one up here. And then we're going to say, convert the grams of copper to moles, and then convert the moles to atoms. So we're doing it all in one step. I think what we're doing is we're limiting the significant figures to this. I wouldn't have limited, I would have gone with this one, because that in my mind is a conversion factor. So probably should have had 3 significant figures out there. Anyway, the method's the same. Okay. So concept, yeah, we got time. Concept 2. A 2-liter bottle of carbonated soda has on an equivalent average 0.2 grams of glucose per 100 milliliters. Glucose is metabolized in the human body according to this equation. That's glucose. And our body converts it to carbon dioxide and water. Use the following steps and the associated equations to determine the number of grams of carbon dioxide produced after the consumption of 10 2-liter bottles. Okay, what's the balanced equation? We've got to balance that equation. It should be fairly easy. Right, 6 carbons. That gives us 12. Well, let's do hydrogens. 12 hydrogens. So 6 oxygens, 12 oxygens, 18 oxygens. And we have 6 carbons, 12 hydrogens. Okay. So now I need, how many? It says 12, 6, 18 oxygens. Well, I got 6 here already. So 12 more will balance it. So that should be down here. Right. There's our balanced equation. If you feel more comfortable in the beginning, set up your budget. That's a foolproof way. Now, if we're given 0.2 grams of glucose per 100 mils, and we want to convert that to liters, right? So this cancels the milliliters and gives us grams per liter. And then this is how many liters, 20 liters. Because we're 10 2-liter bottles, so that's 20 liters. Cancels the liters, that gives us grams of glucose. This is the molar mass of glucose. So that's moles of glucose. And moles of glucose is related to CO2 by 6 to 1. So there's 6 carbon dioxide for every mole of glucose. And then, now that we know how many moles of glucose, we need the molar mass of carbon dioxide. Excuse me, how many moles of carbon dioxide? Molar mass of carbon dioxide gives us 59 grams of CO2. So after you consume 10 2-liter bottles of pop, you're going to exhale 59 grams of CO2. And I'm sure that's got the greenies in a tizzy if they knew that for a fact. We'd have to just keep our mouth shut. Okay, that's it.